This is the lecture on confidence intervals to estimate a population mean. This is going to be very closely analogous with the last lecture, estimating population parameter, the population proportion with a confidence interval, but instead of being based on lecture 16, this is based on what we learned in lecture 17, which I'll review. Given a numerical variable x, let's suppose we know the mean mu sub x and we know the population standard deviation sigma x. We're going to take a sample of size n from the population, and remember there were three assumptions. It had to be a simple random sample, the population had to be at least 20 times the sample size, and the 0, 15, 40 rule had to be true. X known normal, n at least 15, and x is not too skewed, or n at least 40. All those assumptions are met, then we know three things. The sample mean x bar is normally distributed with a mean mu of x and a standard error of sigma x over the square root of n. That's what we're going to use. But now we're going to drop that assumption that we know the population mean. In fact, we're going to imagine we'd like to estimate it. We'd like to use the results of one sample to guess what the population parameter, the population mean, could have been. So let's say we want to know the average cost of the last haircut of all American college students. We're going to take a simple random sample of 50 college students, and we're going to get a sample mean x bar of 35 and a standard deviation, sample standard deviation of 30, let's say. So what values for the mean mu of x, the population mean, are plausible? Well, we know x bar is 35 is our point estimate for mu sub x. It's our best guess from the sample of what mu sub x should be, but we'd like to know what are plausible values. We're going to follow the reasoning in the last lecture to find a confidence interval. So first, imagine we knew the population mean and standard deviation. If all the assumptions are met, we know that if we take many samples of x bar, many samples and compute x bar would have a normal distribution with a mean mu and a standard error sigma over the square root of n. In particular, that tells us that in 95% of such samples, the sample mean x bar would be within 1.96 standard errors of mu. So let's say that over again. The same trick of reversing the perspective, that means in 95% of such samples, the population mean would be within 1.96 standard errors of the sample mean. So in 95% of such samples, the population mean, the thing we want to know, would be in the interval x bar plus or minus 1.96 sigma x over the square root of n. That is a 95% confidence interval for the population mean, which is wonderful, except for one problem, which is that we generally don't know. It depends on the population standard deviation sigma x, and we generally don't know that. It's rare that you would know the population standard deviation and not know the population mean. Happens every once in a while, but it's so rare that we can largely ignore it. So what do? We need a trick. Just like in the last lecture, we used a trick. But the obvious thing to do is to replace the population mean, which we don't know, with our best guess from what we do know. That is, with the point estimate. And the point estimate for the population standard deviation is the sample standard deviation s. So we're going to replace sigma, the parameter, with s, the statistic. The problem is, when we did that in the last lecture, we had an argument that this would not change things very much. The argument doesn't work here. If n is small, s does a bad job of approximating sigma. It can differ substantially from the population standard deviation, so that means when we replace sigma with s, our interval will frequently miss the population mean. It will, in fewer than 95% of samples, contain the population mean. The cost of that added uncertainty is that we're not as confident. So to get a 95% confidence interval, we have to make that interval bigger. So to pay for replacing sigma with s, we have to make that number 1.96 bigger. Remember, 1.96 was called the critical z-value, z star sub c, where c is the confidence level. It's a different one for each confidence level. This larger number we're going to call the critical t-score, and we're going to call it t star sub c. But it's going to depend also on the sample size, and here's an annoying wrinkle you shouldn't get too hung up about. Basically, for historical reasons, instead of expressing it as depending on the sample size, we express it as depending on the sample size minus 1, which we call the degrees of freedom. For now, that's just an idiosyncratic way to talk. Later, we'll start to see a little bit about what degrees of freedom mean, and if you go further in statistics, degrees of freedom will become your friend and an important concept. Right now, what you need to know about T star is only a couple of qualitative facts. Specifically, T star is bigger than Z star because we had to expand the interval to account for our uncertainty. It's much bigger if n is small, and it's just a tiny bit bigger if n is large. So for example, in our case where n was 50 and we wanted a 95% confidence interval, we would compute T star sub 0.95 confidence level as a decimal, comma 49, that's the sample size minus 1, that works out to be 2.01, which is just a little bit bigger than the 1.96 that we would have used if we had known sigma. So all of this together tells you that the C confidence interval for the average value mu sub x of x in the whole population is x bar plus or minus this T star score times s over the square root of n. I haven't yet told you how to find T star. But since I told you this particular value, we can finish our example. Right? We know that n was 50 in our case for haircut costs, x bar was 35, and s was 30. So the 95% confidence interval for the average haircut cost of all college students is 35.0 plus or minus 8.53. We put in our T star score of 2.01, our s of 30, and our n of 50. And that sentence that I just wrote down is the standard expression of the confidence interval, and notice that it contains the confidence level 95%, the parameter, which in this case is average or mean, the variable, which is the haircut cost, the population, which is the college students, the point estimate, in our case 35, and the margin of error, which we calculated as 8.53. That's how I want you to report confidence intervals. Okay, so what I left off for you is where this T star comes from. There are three possible answers. The book's answer is to look it up on a table. That's what we did when I was a kid, and there's no reason to do that in the presence of technology. We'll never do that. But be aware the book is expecting you to. Sometimes the wording of online questions will imply that. The second way is Excel has a command. The command is called tinv, should remind you of norminv, and you have to give it two pieces of information in kind of a funny form. You have to tell it your confidence level, but it doesn't want to hear your confidence level 0.95, it wants to hear 1 minus the confidence level 0.05. And you have to give it the sample size, it doesn't want to hear that, it wants to hear the degrees of freedom, which is the sample size minus 1. So that's a little bit annoying, and notice what's involved here is typing that into Excel and also computing the sample mean and standard deviation from a set of data in Excel. That's a little bit more work than we will generally need to do because we'll use a template. In this class, you'll always be able to use the template to calculate the confidence interval for the mean, and that means you'll never have to calculate Tn directly. And I will show you how to do that in a moment. First, I have to tell you a little bit more about this t-score. It comes from the t-distribution. In statistics, it's conventional to refer to probability distributions by letters. Z corresponds to the normal distribution. T is the t-distribution. It is, technically speaking, the distribution you get if you take a normal variable, take a sample x bar, and take x bar minus the mean over the sample standard deviation over square root of n. And what the distribution looks like is pretty much the normal distribution, but with fatter tails and a shorter peak. The black line is the normal distribution. The red and blue lines are t distributions with respectively 3 and 6 degrees of freedom. You can see as the degrees of freedom goes up, the difference from the normal distribution goes down. It approaches the normal distribution. But apart from having fatter tails, it looks pretty similar. It's got an interesting historical story. By interesting, I mean it involves beer. William Gossett was an early statistician. He worked for Guinness doing what we would call quality control. Of course, you have to take a lot of samples and test things. At the time, people just took large enough samples, they didn't even have to notice the difference between S and sigma, so they never thought about these issues, but he didn't want to take large samples because he didn't want to waste the beer. So he developed these tools for taking small samples. He wanted to publish this so other people would know that, and Guinness said, no, we don't want our competitors learning this trick. He published it anyway under a pseudonym, the rather humble pseudonym Student, and still sometimes called Student's T distribution. Okay, I'm going to run through really quickly the description of how to use the template because I'll show it to you and that's much more useful, but I want to have this written down so you can study from it. We will go to the same place we get the template, the histogram template on my website. A little below the histogram template are all the other templates we're going to use this semester. You'll look in the first row, second column for the template called One Sample Mean T Procedure. Usually you'll have raw data and you will paste it, just like you do for the histogram, in column A in the Data tab. Sometimes, instead of raw data, you'll have the mean, standard deviation, and sample size as separate numbers. You'll enter these at the top of the t-test tab, and you'll have to check the Use Summary Stats button. And then, final step is, on the t-test tab, you will enter the desired confidence level, 95% or whatever, and then you just read off the confidence interval, which is in green to the right. Sometimes online questions will ask you for the critical t-value, or the sample standard deviation, or other quantities used on the way to the calculation. Those are all listed there, so you should always be able to find them there. There's also a histogram, or hist tab, which contains a baby version of the histogram template, and we will use this when we're checking the assumptions. Okay, so here's an example. Florida Student Survey, column H contains data about what a sample of Florida college students, how much TV they watch per week. We're going to use that data to give a 90% confidence interval for the average hours of TV watched per week for all Florida college students. Follow along with me on this. On my webpage, we'll click on the Data Files tab, and down here in the Data Files from Agreste Franklin is the Florida Student Survey data. Here it is. It's a survey very much like what I asked you all in the first day. One of the questions is, how much TV do you watch? Column H. We're going to copy that. So literally click on the letter H and do Control or Apple or Command C to copy it. And then we go back to the web page, up to the main page, and click on Excel Templates. So down here, all the procedures we're going to use are labeled by the variable. It can be categorical, numerical. We won't do the ranked variable procedures. We have a numerical variable, and then the rows are how many populations and samples you're taking. We have one sample. So we use the one sample mean, or T procedure. Procedures are traditionally named after their distribution. It opens up on the Data tab, just like the histogram page, where there's dummy data, just like the histogram page. We paste over that dummy data, and now we click on the t-test, and most important, you gotta say what your confidence level is, unless it's 90%. We enter the confidence level, and that's it. Here's the confidence interval. If, instead of telling you the data, I told you the mean is 7.27, the sample standard deviation is 6.72, and n is 60, you would enter that here, and you'd have to click on this to tell it to look there. Okay, so our confidence interval is 7.27 plus or minus 1.45. So let's return. We report that the 90% confidence interval for the average hours of TV watched per week by all Florida college students is 7.27 plus or minus 1.45 hours per week. That's it. It's actually pretty easy to do this. It takes a couple of times to get the hang of it, but there isn't very much to the process. But there are assumptions. So the assumptions are just like the assumptions for the sampling distribution of a numerical variable. There's a little wrinkle to how you check the 0, 15, 40 rule. So, assumption A, it's a simple random sample. Problem has to say it's a simple random sample or else we don't know. Sometimes it'll describe the sampling method well enough you can see that it's clearly not a simple random sample, and you should say that if it's true. Assumption B, large population. Population needs to be at least 20 times the sample size. Usually that's obvious even if you don't know the exact population size. C is the 0, 15, 40 rule. There are 3 ways you can meet it. If the problem says that x is bell-shaped or roughly normal, then you know x is normal. You know the population distribution is normal. You're done. If n is greater than or equal to 15, remember we need x to be not too skewed. Here's the new wrinkle. It turns out, here's the magic thing, that a sample of 15 is big enough that the histogram of the sample will tell you whether or not the population is skewed. It won't tell you whether or not x is normal. That's okay. But if your sample distribution is skewed, then your population distribution is almost certainly skewed. And if your sample distribution is symmetric, your population distribution is symmetric. So, the new wrinkle is, if n is between 15 and 40, you look at the histogram of your data distribution. If n is more than 40, as always, we're done. Let's do another example and we can practice that new wrinkle. So, a file called anorexiafix.xls on my website contains information about a study of anorexic teenage girls. Columns C and D look at a sample of 17 anorexic teen girls who receive a family-based therapy and give their weights before and after the therapy. So the difference, which is in column I, represents the weight gained during the treatment. And it's a measure of the effectiveness, right? The more weight they gained during the treatment, the more effective the treatment was. This is an example of what's called a matched pairs study, where you measure a variable under 2 conditions and use the difference to measure the effect of these conditions. We'll see matched pairs studies once in a while going forward. So we want a 95% confidence interval for the average weight gained by all anorexic teen girls under this treatment. Again, let's escape and go to my webpage. Data files, anorexic fixed. It's not that the anorexia has been fixed, it's that the file had problems and I put a second version up. Let me quickly run through C and D. This is the weight of each girl before and after the treatment. So you see the first girl gained 11.4 pounds. In contrast, this girl went from 76.9 to 76.8. She actually lost weight. It was not effective for her. We want to use all of these weight gains to find the average weight gain, not of the sample, that's just the average. We want to estimate with a confidence interval the average weight gain for all anorexic teen girls who might use this treatment, which is the effectiveness of the treatment. We capture the data, we go to the Excel templates page, download a template. You can reuse the old template, but every once in a while it gets you into trouble. So the careful thing to do is, careful thing to do is to get a new copy, paste your data into the data tab, and enter the confidence level. In this case, it's 95%, so the confidence level is already entered, and we read off our confidence interval, 7.26 plus or minus 3.68. Down here are all the things that online homework might ask you about. For example, there's the critical t-value. Notice it's more than 1.96. It's substantially more this time, because our sample size of 17 is pretty small. But all you need to take away is the 7.26 plus or minus 3.68. And let's go and look at our answer and hope that we got the same thing. Yes, the 95% confidence interval for the average weight gained by anorexic teen girls under family therapy is 7.26 plus or minus 3.68 pounds. Now let's check the assumptions. Simple random sample, look through the question, and it doesn't say, so it's not met. Large population, we'd need there to be more than 20 times 17, more than 340 anorexic teen girls in America, the world, I don't know, but that seems safe. 0-15-40 rule, this is tricky, right? Nothing in the problem says that the variable is normal. Variable amount of weight girls gain is normal. And n is less than 40, so we don't meet versions 1 or 3. Only hope is version 2. 17 is more than 15, so we're good as long as the data is symmetric, is not too skewed. And how do we check that? We check it in the histogram tab. Here's a histogram of our data distribution. If the data distribution is reasonably symmetric, which this is, it's safe to assume that the population distribution is as well. I would call this data very slightly left skewed, but really hard to tell even which direction it would be skewed. This is reasonably symmetric, so the assumption is met. Really important. That distribution, whether or not you think that looks normal, that doesn't tell you if the population distribution is normal. You'd need hundreds of data points for the data distribution to give you a reasonable indication of the normality of the population distribution. But it is good enough, if n is at least 15, to tell if the population distribution is highly skewed or not. So this, we meet the 0-15-40 assumption. Okay, I want to end by reminding you of what the confidence interval means. Most importantly, what the confidence level means. The 95% confidence level is a probability, and probabilities always tell you how often something happens in repeated tries. You don't understand a probability unless you know what the thing is being repeated in your case. In this case, the thing you're repeating is taking a sample and using it to compute an interval. Okay? So the process, the random process is you pick a random sample, you compute a confidence interval. The 95% says that 95% of samples, when you apply this process, will give you an interval that contains the population mean, or in general, the parameter that you're trying to approximate. So your interval is one of all the thousands you could produce from all the thousands of different samples there are. In that sense, your interval has a 95% chance of containing the correct value. It's a funny way to think. In particular, although we don't know the population mean, we'll never actually know it, it is some fixed value. There is some number that's the population mean. So it's not varying. It's not a probabilistic concept. It's the interval which is varying and may or may not contain that fixed unknown number. Other important pitfall to avoid is with a numerical variable, you might think that that 95% confidence interval, 7.68 plus or minus 3.5, whatever, is an interval such that 95% of the values of x fall within it, that 95% of teenage girls gain weight in that interval. That is not true. It isn't what it tells you. Okay, here's what you should have processed from this lecture. You should be able to use the template to find a confidence interval given a confidence level, and either given data or given the mean standard deviation in the sample size. More practice on that is available if you look at the examples lecture. You should be able to express that confidence interval in a sentence which identifies the confidence level, parameter, variable, population, point estimate, and margin of error. This is old hat. We've been doing that since the first confidence interval lecture. You should be able to check each of the three assumptions: simple random sample, large population, 0, 15, 40. Again, that should mostly be old hat. There's this extra wrinkle in the 0, 15, 40 rule. The middle assumption, you can check the actual data to test. You should keep straight the difference between a confidence interval for a mean, what we just learned about, associated with a numerical variable, versus a confidence interval for a proportion, what you do with a categorical variable. That's the previous lecture. Two different procedures in two different situations. Finally, you should be able to interpret the confidence interval. Remember, the interval is the set of plausible values for the population mean, and the confidence level describes the proportion of all samples whose confidence intervals produced in this fashion contain the population mean.